Okay, so from this video, I will talk about the derivatives. Okay, until I talk about integrals. So everything will be related to the derivatives. So what is derivative? It is the instantaneous rate of change of a function at a point. So maybe we can take a look at the sine function, okay? So by the way, I'll ask this question, I asked this question in my tutorials, but I want to ask this question here as well. So which one is the correct graph of sine of x? I just draw like a part of it. Which one is the correct graph? Well, in my tutorials, many students will just say, well, what's the difference? They seem to be both the sine function. I don't know which one is correct. But if it is like in the correct scale, then only one of them is correct. And I would say that the second one is the correct sine function, while the previous one is not. So the problem is around 0, if you look at the graph of sine, and then if you have like some softwares like Desmos, right, the graphical calculator, then you can just sketch the graph by putting the y equals sine of x or things like that. And then if you zoom in the graph a lot, then you see that around this point 0, this is almost y equals x, right? So this means the tangent line of x at this point, x equals 0, is y equals x. Which means, locally speaking, this graph, so sine of x is approximately x. So this is correct, because we just said in the previous lecture, right? In the previous video, that this should be equal, right? I mean, this should be approximately equal. So which means the slope of the tangent line should be 1, okay? So which means if you look at it close enough, then it should be of this angle, which is 45 degrees, or pi over 4. But if you look at this graph, then the slope seems to be bigger, right? Or this angle is much bigger than 45 degrees, so this is wrong. So this basically gives a very good introduction to the notion of derivative. What is the derivative? Well, we just look at some point just here. In general, we can, let's say, look at some point, maybe over here. Let's say this is A. And then what's the definition of the tangent line? Or what's the definition of the slope of the tangent line? Well, we cannot define the tangent line directly. We actually can, but it's much more complicated, and you will learn it later. But here, we all need to look at all the points that are close enough to it. So let's look at A plus H, right? So this will be a secant line. And then we can tell from this H, so if you are given some small h, so this can also be negative, right? This also can be negative. So when I say small, I mean this is the absolute value is small. So which means this will be less than some epsilon. You just look at some h that is very small, or you are looking at some x that is close enough to A. Okay, then you can calculate the slope of the secant line, which is f of A plus h minus f of A divided by h, right? You should have no problem, because the increment of x is h. The increment of y is, this point is f of A plus h. This point is f of A, right? I'm talking about the y value. So then the increment of y would be f of A plus h minus f of A. So if we look at this triangle, then the tangent of this angle is equal to the slope of the tangent line, of the secant line. And this is equal to f of A plus h minus f of A, which is the increment of y, divided by the increment of x, which is h. So then we can look at all this h, and because we have defined what the limit means, so we just want to look at if the limit exists when h approaches 0 from both sides, right? We can also approach from the left-hand side. So we'll look at this secant line. And you'll notice that for this graph that is smooth enough, or let's say it's differentiable, when h approaches 0, you can see that the slope will converge to some fixed value, and this value is called the derivative. Okay, so if this limit exists, then we say the function f is differentiable at this point a. And then this value is denoted by f prime of a, called the derivative of f at the point a. Okay, this is called f prime of a, which is the derivative of f at a. And so this gives you a notion of derivative. Okay, so this is a definition of the derivative. So maybe we can just take a look at the sine function. So let's see if the sine prime of 0 is 1, right? What does it mean? It means that if you look at the sine function around 0, if you look at the tangent line, then the tangent line should have a slope 1, right? Because this is what it means for y equals x. This means the slope is 1. So this, and also the slope of the tangent line is equal to the derivative of this function at the point. So then we want to show that this is equal to 1. So then this will show that this is the correct graph. And you will immediately notice that this is exactly what we have discussed in the last video. Because by definition, this is the limit as h approaches 0 of sine of h minus sine of 0 divided by h, right? And also we know that clearly sine of 0 is equal to 0, so we don't need to write this term. So this is simply the limit of as h approaches 0 of sine of h over h, and this is 1, right? We don't care about the symbol, it's just some variable that approaches 0. So we can change it into x, right? Then you become more familiar with that, but it's the same. So what it says is that this limit actually is equivalent to saying that the sine function has derivative 1 at 0. Okay, so the derivative at 0 is 1, which means this is the correct graph. And also, because you know the tangent h over h will approaches to 1 as h approaches 0, so you have exactly the same thing. So if you look at the graph of tangent h, this is minus pi over 2, this is pi over 2, then around here it must have this this slope, which means this should be something like this, right? So this is the correct graph. Well, for example, let's say this is not the correct graph, right? Because here the slope is almost 0, but here this is correct, the slope. This should be 1. Okay, does that make sense? So the reason is that the derivative of tangent at 0 by definition is equal to the limit as h approaches 0 of the function evaluated at this point plus h minus the function evaluated at this point 0 divided by h. And then this is simply, and also we know that tangent of 0 is 0, so this disappears. So then the limit as h approaches 0 of tangent of h divided by h is clearly 1. So this means the slope of the tangent line should be 1. Okay, so maybe we can do a simple exercise. So maybe we can try to find the derivative of x squared. So we denote it by this. Okay, so which means given f of x equals x squared, we want to evaluate the derivative of f at any point x. Okay, so we're asked to find this f prime of x. So by definition, the derivative of f at x is the limit as h approaches 0 of f of x plus h minus f of x divided by h, right? So we can simply plug in a value. So then this is, so f of x is equal to x squared in this case. So it is the x plus h squared minus x squared divided by h. While this is the numerator is equal to, because x squared cancels out with this x squared, so we only have two terms, which is 2xh and h squared, right? And then we can cancel out this h, so this becomes the limit of 2x plus h. And now, because we're taking limit with respect to h, so this x is a constant, right? Because it has no h in it. So we can think of this as some c. So which means we can just, and also when h approaches 0, this clearly approaches 0. So which means this should be equal to just 2x, right? Because if you want to write it rigorously, then it is the limit of 2x plus the limit as h approaches 0 of 0. And you can write in this way because both limits exist. And this is a constant, so this is 2x, and this is 0, so this is 2x. Which means the derivative of x squared, for simplicity, which is denoted by x squared prime, okay? The derivative of x squared at x is equal to 2x. And in general, we can show that x to the power of n, if you take the derivative, then it's going to be n times x to the power of n minus 1. So here, so if you want to memorize this, you just put this n down into a constant, and then you decrease this by 1. So for example, what is the derivative of x to the power of 4? This is 4 times x to the power of 4 minus 1, which is 3. And then x to the power of 10, if you take the derivative, it is equal to 10 times x to the power of 9. Okay? And this is also true for square root of x, for example. Because if you want to take the derivative, this is x to the power of 1/2 when you take the derivative. So this is going to be, you still do the same thing. So you put this 1/2 to be the constant times x times 1/2 minus 1, right? So this is 1/2 times x to the power of minus 1/2. So it is minus because then it is in the denominator, and then 1/2 means square root. So this is 1/2 times square root of x. Okay, which means this is very, very important. The derivative of root x is 1/2 times square root of x. This is very important. And basically, you can just play with it, and maybe you can look at what's the derivative of x to the negative 3, right? And it's negative 3 times x to the power of minus 3 minus 1, which is minus 4. Okay, so this means the derivative of x cubed is equal to minus 3 over x to the power of 4. So you just play with this formula, and you can get, for example, the derivative of 1 over x is, because it's x power 1 minus 1, so you have minus 1, and then minus 1 becomes minus 2, so this becomes minus 1 over x squared. And you can just play with it, and then this becomes negative 2 over x cubed. Okay, so in general, if you want to have 1 over x to the power of n, then you can find a pattern. If you want to take the derivative, this is negative n over x to the power of n plus 1. Why? Because this is x to the power of negative n, so then you put negative n here, and then you have x to the power of negative n minus 1. And this becomes x to the power of n plus 1 in the denominator. Okay, so this is minus n over x to the power of n plus 1. So you should be familiar with these formulas, although they are very easy. And also, I should mention a simple formula. So what is the derivative of a constant function? Okay, so if this is a constant function c, then we want to find some tangent line. Well, this is already a line, so the tangent line must be also horizontal. And then the slope of a horizontal line is always 0, which means the derivative should be 0 everywhere. So this means if f of x is equal to some constant c, then f prime of x is equal to 0 everywhere, which means, simply speaking, c prime is 0. So the derivative of a constant function is 0 everywhere. So let's prove this fact. We'll just use the definition as h approaches 0, f of x plus h minus f of x divided by h. This is going to be the limit as h approaches 0 of, because it's a constant, so it's a constant everywhere. It's independent of x. So f of x plus h will be the constant, and f of x will also be the constant c, which means this is 0. Okay? And then the limit of 0 is clearly 0. And one might ask, what if h is equal to 0? We don't care about that, because h approaches 0. When we take the limit, h will not be equal to 0. Okay? So h will not be equal to 0. So then this is well defined, and then 0 divided by any number is 0, which means this is the limit of 0, which is clearly 0, because it's the limit of a constant 0. So then it's 0. So it makes sense. So like if you have a graph like this, that is a constant function, then whatever the point you are looking at, the tangent line of that will always be exactly the same thing. So then the slope of the tangent line will be 0 because it's horizontal. Okay. And then if you okay, so here you have so one might ask, what's the relationship between differentiability and continuity? So luckily they have some relationship. What we can show is that if f is differentiable at a, then we must have that f is continuous at a. It makes sense because like locally, you can find some linear line that can approximate the graph very well. So it should be at least continuous because continuity is not so much. Okay, so let's prove it. Okay, so we want to show that the limit as x approaches a of f of x is equal to f of a. So this is equivalent to say we want to show as h approaches 0. So we use h to denote x minus a. So when x approaches a, this means equivalently speaking, h approaches 0, right? So all we need to show is that, and now if we write h as x minus a, then x will become a plus h, right? So we do this change of variable to change from the limit of x into a limit of h, okay? So then f of x will become f of a plus h. And then this is still f of a. So all we need to show is that the limit as h approaches 0 of f of a plus h will be f of a. And this is very, very familiar because if you, and also equivalently speaking, all you need to show is that the difference, as I mentioned in the previous videos, all you need to show is that the difference of f of a plus h and f of a is 0, right? The limit should be 0. And then, what it means for f is differentiable at a, so now we can put in this way. So now we can really start this question. So we can say since f is differentiable at a, we have the limit as h approaches 0 of f of a plus h minus f of a divided by h exists, right? It is equal to some f prime of a, and it exists. It is some real number, right? It is some real number. And then we're asked to find what's the limit of this term. Well, we can just simply rewrite this f of a plus h minus f of a as we first divide it by h and then we multiply by h. Okay, so this is a common trick, but it's a very simple trick. So if we want to take the limit of h approaches 0, then we can simply take the limit of that, and then we can show that the both limit exists. So then we can use the product rule to rewrite this as the limit of this term times the limit of the next term. And then what we have is that because f is differentiable, and here it's crucial that f is differentiable, otherwise this limit will not exist, okay? So because f is differentiable at a, so this will exist, and then this is equal to, this limit is equal to f prime of a by definition. Well, this must be 0, clearly, and then 0 times any real number is 0. Here f prime of a has to be a real number, so it's okay that we have this is equal to 0. So this means that this will converge to 0, or f of a plus h will converge to f of a as h approaches 0, or it means when x approaches a, f of x will approach f of a. So here, let me emphasize. So it is quite interesting that we can do some change of variables, and you can prove it rigorously, but I don't have time today to talk about that. And you can actually form a similar definition of the derivative, okay? So it is an equivalent definition of derivatives of a derivative. So f prime of a can be defined as the limit as h approaches 0 of f of a plus h minus f of a divided by h. But also you can think of you can do the change of variable into x approaches a, because basically you are looking at a plus h, right? And when h approaches 0, this is just some number that approaches a. So you can call this number x, which means here you do it the other way around. You say x is equal to a plus h. And then you want to switch this h as well. So then h will become x minus a, right? So if you want to do the change of variable between h and x, then this becomes the limit as x approaches a of the quotient of, let's say, f of x minus f of a divided by x minus a. And it makes sense because geometrically speaking, you have a, and then you just look at some x that is close enough, right? And then you look at the secant line. So then the increment of x will be x minus a. The increment of y will be f of x minus f of a, because this is f of x and this is f of a. So it's the same. The only difference is the variable. So we can apply the simple change of variable. It's kind of like a linear change of variable. So we can solve from h to get x, we can solve from x to get h. So then these two are equal, or they are equivalent. And you can show that they're equal rigorously. But as I said, I don't have time today. Okay? And sometimes this will be more useful, and sometimes this will be more useful. Just you have to be clever to use the correct version. And let me continue. Okay, so maybe I will talk about some simple rules of differentiation. So let me talk about some differentiation rules. So first we have discussed that the derivative of constant is 0. And then we have discussed that the derivative of x power of n is n times x to the n minus 1. And also we know that similarly x to the power of minus n, or 1 over x to the power of n, if you take the derivative, it is minus n over x to the power of n plus 1. Okay? And then you can look at, for example, you can look at the derivative of f plus g. You can prove that it is equal to f prime plus g prime. So like the derivative of a sum is the sum of the derivative. And also it's the same when you change the plus into minus. Okay? And also if you have a constant c, so if so here I have said that c is a constant. Okay? So if c is a constant, then c times f, if you take the derivative, it's going to be c times the derivative of f. Okay? But if you want to multiply two different functions, then it will not be that simple. Okay? So if you take the derivative of f times g, it will exist, but it is not equal to f prime times g prime. Okay? It's a big mistake. You can only say that this is equal to f prime g plus f times g prime. Okay? So you can actually prove it, but I don't have time for today. So this is called the product rule. And you have to memorize it. Okay? And also you have the quotient rule that is also different. These are very important. So the quotient rule says that the derivative of f over g is equal to the quotient of f prime g minus f g prime divided by g squared. And definitely you need to do some practice. Okay, I'll just show it here that you can use this quotient rule and also the product rule. Okay. Okay, and then if you want to generalize the product rule, you actually have that the derivative 3 times. If you take the derivative, you can actually show that you can think of this as f times gh, right? Then this is going to be the derivative of f times gh plus f times the derivative of gh, and then you apply the product rule again. This becomes f times g prime of h plus g times h prime. So then you will get this is equal to f prime gh plus f g prime h plus f g h prime. So you can see that you have 3 terms. So each time you take the derivative with respect to exactly one function. So you take the derivative of the first function times the other 2. You take the derivative of the second function and then you multiply the other 2. And then the same thing happens with the last term. So you can prove actually by induction. So by induction, one can prove that the derivative of a product of f1 up to fn is equal to, as what we expect, f1 prime times f2 all the way up to fn plus f1 times f2 prime all the way up to fn plus all the way up to f1 up to fn minus 1, and then we take fn prime. Okay? So this is the formula. I mean, this is a generalized version of the product rule. And one might ask, what is the generalized version of